Hey, Hoger.
Hello. So I hope it's okay to record today's presentation and make it available online afterward. Now you are unmuted. Can you hear us? We cannot hear you yet. Hello, still working on it. Now we still have a couple of minutes. The chat is open if that's useful.
All right. Barney, are you there?
No audio yet, even though you are unmuted. Just a minute, all right.
How's that working?
Now we can hear you. Hello.
Hello, sorry about that. I'm using my work computer and they, I think, had some kind of security setting, which I was not ready to try to figure out how to fix right now. So I went ahead and just downloaded the Zoom app and went on the Zoom app.
All right, that works. So is it okay to record this and make it available on our website? All right.
Absolutely.
Thank you.
So Barney, welcome, and thank you for agreeing to give a talk. Every spring semester, Wichita State University Physics has a special seminar that involves, someone who's not exactly maybe going to present research, but we had my editor of one of my books come and talk about how to publish science. We had a film producer who I worked with once come and talk about how to make films about science. We've had other people come and talk about careers in science that are both academic and non-academic. And what had happened was about 6 months ago, I was cleaning up a corner of my lab. And in there, I found this photograph, which is sitting up here behind me. And I say, well, that person looks familiar. I mean, I met the Lawrence Livermore National Lab Director once, and it kind of resembles him. And so I wrote, and it turned out, well, it's not exactly you, it's your grandfather.
Right.
And he was chairman of physics here back in the 1960s. He also won Best Teacher of the Year award 5 times. He actually had to share the award the last time. This was in it was the year he retired, 1960 something, according to a Sunflower article. And he was a little bit disappointed that he had to share the award the 5th time, because he thought they should have just gave the award to the other person because he already had it 4 times. So, well, that shows you. And then, of course, I had a discussion with Barney online through email. It turns out that his grandfather was very inspirational to him. As the chairman of physics, he knew about science, and he was able to direct Barney into the excitement and the thrill of doing science and engineering. And of course, that led to your career. So in some ways, you're kind of like a native of Wichita in some ways, because your grandfather was here. In other ways, you set your own unique path in your own career. And Barney, who has been the director of Lawrence Livermore National Lab, as the director now of HRL Lab, and I think that's Huge's research lab, right?
It's the old Hughes Research Lab. Yeah.
Right. They changed their name. Yeah. And he's going to be talking today about his career in physics, which is outside of academia. And we have a lot of undergraduate students and graduate students in physics that are here. And as you know, not all students go into academia or national lab research. And there's a huge demand for physicists and science and engineers in the world of non-academic labs. And so we're going to hear today from Barney Albright, grandson of our former physics chairman from the 1960s here at the University of Wichita. And we actually changed our names also. We're now Wichita State University. He's going to be talking to us about some reflections on a non-academic career in physics, with examples from some of the projects in which he's been involved with and some of the broad lessons he's learned. So everyone join me in welcoming Dr. Barney Albright.
Thank you very, very much. I appreciate it. This is, it's really an honor for me, right? I haven't, to do this at the place where my grandfather taught and in the city that my dad and his brothers grew up in. It's, I still remember, although I have to say it's very vaguely, visiting my grandfather. He took me on a tour of the labs at the University of Wichita, which is what it was, as you said, was what it was at the time, and showing me some of the labs. I think I was 6 years old at the time. And so that was over 60 years ago. Most of the time, my grandparents came to visit us in Washington, but yeah, I think this will be maybe a little bit of an unusual seminar, both for you and for me. For you, as you pointed out, this is not going to be a technical talk. I'm also not going to use any PowerPoint. I'm just going to talk. But I will try to maybe weave in a few technical anecdotes from my time over my career. And for me, it's pretty unusual because I can't remember the last time I think I spoke to a academic audience of any significant size was maybe 20 years ago. And it was at a joint National Academies AAAS meeting. And I was on the White House staff and I was kind of giving them a hard time. So, and if you really want to know what it was about, you can ask me during the Q&A. But so it's a bit of, this will be unusual for me as well. What I thought I would try to do today is, rather than make this an autobiography of my career, which I think would bore you to death, what I'm going to try to do is give you some insights into what an non-academic career in physics can look like. As I said, with a few personal anecdotes sprinkled in. And the other thing I'm going to say right at the outset is that what I'm going to talk about is heavily colored by having a PhD. I have a PhD, and that's been my experience. At HRL, by the way, they're in the latest issue of Physics Today, which I'm sure everybody here gets. There was actually a really good article about the Southern California Industrial Research and Development Laboratories, and HRL it was the old used research lab, is featured prominently in that. It's probably I thought it was a pretty interesting read. And we do hire at HRL students, graduates with bachelor's and master's degrees. They generally operate test or measurement kinds of things that we do. But again, my experiences are those with a PhD. And I guess the other thing I would also say is that I have spent almost my entire professional career in the national security space. Actually, even at HRL, we're jointly owned by Boeing and General Motors, and we do quite a bit of commercial work. Obviously, General Motors is a commercial firm, and Boeing has a very significant commercial side to it. But my personal career has been in national security for the most part, and that's where really a vast number of physicists are employed today. But again, I'll try to say a few words later on about sort of the broader industrial experience. But anyway, that's my background. And because of that, if the national security space is generally not open to non-US citizens, but there's plenty of jobs out there in the industrial space for non-US citizens. And again, as I said, I'll say something about that. So first of all, let me sort of address how did I kind of end up doing what I was doing, what I did. I got my PhD at the University of Maryland in College Park, and at the time, I was actually the president of the Physics Graduate Student Association, and we had a department chairman who was actually fairly forward-leaning. And so he brought me into a lot of the conversations that were going on, in particular surrounding things like tenure decisions that were being made in the department. And at that time, I was married, I had a 2-year-old, and I just made the decision that I was not interested in pursuing an academic career because I didn't want to go through the whole, assistant professor, process that you have to go through to get tenure. But I did do a postdoc, and I was sort of ending my postdoc and was trying to think about what to do. And right around that time, the book, the hardcover version of the first Tom Clancy book, The Hunt for Red October, came out. And for those of you who don't know the story of The Hunt for Red October, there's also a movie been made of it. It's basically about a CIA analyst who just gets to do all kinds of cool things, right? And I remember thinking to myself, that would be a really cool job. And so I started interviewing with a set of entities that are called FFRDCs, Federally Funded Research and Development Centers. And they're probably, most of the people here I'm talking to probably have no idea what those are. So let me spend a moment to talk about them. First of all the Department of Energy national laboratories are FFRDCs. So like Lawrence Livermore, Oak Ridge, Argonne, Brookhaven, they are all FFRDCs. They're nonprofits, and they are mission focused. Lawrence Livermore's mission is nuclear weapons. Oak Ridge's mission is fundamental science, for example. Brookhaven tends to focus on particle physics. So they all are asked, they have missions. The Department of Energy operates a whole bunch of these, but there's actually a whole bunch that the Department of Defense operates as well. And you may have heard of Lincoln Laboratory up in Bedford, Massachusetts. They have been around for a very long time, and initially started in World War II to work on radar kinds of things. And they actually support the Air Force. You may or may not have heard of the Aerospace Corporation here in Los Angeles. They basically now support the Space Force. They are all about supporting satellites and launch vehicles. And their whole mission is basically all these FFRDCs basically have a mission to maintain a set of core competencies in particular areas. And I ended up at a place called the Institute for Defense Analysis, which was really designated as the sole support for the Office of the Secretary of Defense. And actually the origins of that FFRDC are kind of funny. It was started by President Eisenhower because he was really irritated by the fact that the Air Force had their own FFRDCs, the RAND Corporation at the time, and we're talking up something called the bomber gap and the missile gap, which if you read the history of the Kennedy and Eisenhower era, were sort of very big controversies. And there was nobody who was kind of objectively speaking for the Department of Defense writ large. So anyway, that's where I ended up. And it turned out to be probably the best career decision I ever made. But before I start going into some of the history, let me just sort of tell you a little bit about what I think a physicist does, particularly a non-academic physicist. So first of all, at the end of the day, physicists have generally a particular expertise in a particular area. At HRL, if I'm looking for someone who is an expert in lasers, or I'm going to go find someone who did a graduate degree or maybe a master's degree in laser physics, or material science, or whatever. But more importantly, physicists are very capable mathematically. It's one of the reasons why Wall Street is so keen to hire physicists out of school, because they just really tend to be very good at applied mathematics. And in particular, physicists are very good at what used to be called, when I was in school, word problems. And what do I mean by that? It means that a physicist knows how to separate the salient features of a particular problem from the heat bath, right? What are the things that are going to matter? And what are the things that might even be interesting, but are really sort of second order or third order effects? And I can, at least for the moment, try to ignore those. And then the other part of that is that physicists know how to start with a simpler problem and then perturb their way around that to sort of see the effects of additional complexities. You know, a lot of jokes are made about physicists assuming spherical cows. But in fact, you can actually get a lot of insight, I guess, if you assume a spherical cow. And what that really does is it provides you with a terrific intuition, because when you build these simpler models in your mind, and then you're faced with a real problem, you can test that against a simpler model, and you actually have a scaffold around which you can sort of build your understanding of what's going on, and test ideas. And I can't tell you how many times I have sat in meetings where people are briefing on something, and I just look at it and I go, you know, that just doesn't sound right. Right. And that's the way you develop. And I would just say that physicists are almost uniquely, as a discipline, geared up to think in that way, right? To simplify problems, to build intuition, and then have the mathematical tools to do something with it. I will say that this reinforced, in my experience, this was reinforced over and over and over again, both personally and with people who I have worked with and led. It is just an attribute that comes with having a physics degree. Because of that, so if you go into a non-academic career, it is entirely possible that you could spend your entire career working on your specialty. If you are a materials scientist who specializes in steel alloys, for example, you could go work at Boeing and spend your entire career doing nothing but that. Or if you're a solid state physicist and you want to work on gallium nitride, you could spend your entire career doing that. It kind of depends where you go but if you go to a place like I did, which was an FFRDC that was really doing studies and analysis of weapon systems, you will generally not have anything relevant to what you got your PhD actually in. My PhD was in renormalization group theory, which back in the 80s was kind of a hot topic, not so much anymore. The first assignment I got when I showed up to work was to actually become an expert on rocket plume phenomenology, ballistic missile plume phenomenology. And this actually dealt with the optical signatures associated with the ballistic missiles when they launch. And there's all kinds of interesting problems there. There's equilibrium and non-equilibrium chemistry. There's supersonic flows. Atmospheric chemistry plays a significant part to all of this. I knew absolutely nothing about this when I first showed up to work. But at the end of the day, the principles were certainly understandable. You could pick up a book on hypersonic flows or supersonic flows, and it's not that, you can, based on your physics background, you sort of understand what's going on. You can pick up a book on reacting chemistry and turbulent flows, and you can understand, again, you have the right kind of background to figure that out. And I will tell you that within about a year and a half, I was actually considered to be a world's expert. And that led to a lot of cool things. The first thing was that I actually got to be the principal investigator on a space shuttle mission, STS-37, by the way, which is, tells you how long ago it was. And I will tell you that to this day, almost 40 years later, I maybe 3 or 4 times a year get calls from people trying to pick my brain on this particular topic. And so what that leads to is, I guess, my first piece of advice to anybody pursuing a non-academic career. And the term we used to use back in those days was, it was called "make your bones." And that's a term from the Godfather book and movie. And what it means in this context is that you really need to become an expert at something. Because once you do, the opportunities will flow. For example, I was involved with ballistic rocket plume signatures, optical signatures, but that's, you would go to meetings and, you would be part of a process that was maybe developing a weapon system, and the parts associated with that system. In those days, strategic defense initiative was a big deal. People were talking about putting high energy lasers in space. By the way, a really dumb idea, but nevertheless, that's what they were talking about doing back then. And the signature against which they would target the missile was actually the rocket plume. But anyway, I got involved with high energy lasers, and I got involved with kinetic kill missiles, and over time you just get exposed to an awful lot of things, but you don't get into that environment unless people think you can contribute, and having expertise in an area is really very important. One other thing that happens is that once you become an expert, you will tend you'll be asked to provide advice to stakeholders. And these are often government officials, that was the case in my career, or in a commercial firm, you might be talking to the CEO. And there's a couple of aspects to that. One is that you have to absolutely know how to communicate sometimes complex things in ways that a lawyer will understand, because these are generally people with law degrees or business or poli-sci. And then the other thing is you will often get embroiled in controversial issues. I mean, after all, the reason you're there is because they're looking for advice, and if the reason they feel they need advice is because there's some controversy on the table. And if you're working in the trenches, if you're early in your career, this will not happen very much. But as I said, once you generate some expertise, it will happen to you, and it will happen all the time. And even to this day, I have responsibilities running HRL laboratories, but I am routinely asked to come to Washington, and in fact, just happened yesterday, and participate in helping the government work through a controversial issue. But why is the issue controversial? Well, the reason the issue is controversial is because usually someone senior has committed to what was probably, at least somebody thinks, is a dumb idea. And there's usually budget attached to it, whether you're in a commercial firm or in the government. And then what happens is, because of that, questions start to be asked: is this really a good idea? And so a big part of the job of being a scientist in a commercial or industrial firm of some kind, of any kind, is to be a technical, honest broker. It is to be objective and not worry about the reaction from the advocates. I will tell you, or actually this happened early in my career, I literally had a government official leap across the table to try to, I wasn't sure what he had in mind, because he was responsible for a particular computer code that I showed from data was off by 3 orders of magnitude. And he probably no one had told him that before. But yeah, you got the advocates they're not gonna like you, but nevertheless, your job is to have integrity, and that can't be an issue in a non-academic environment. As I said, early in your career, you might be involved in a project that is very, very specific to a component of something that's interesting. It might be a very interesting technical problem, but the overall thing that you're working on may not make a lick of sense. And it's sometimes hard to give good advice in that case. And it happens more often than you think. Except I would just say that at some point in your career, as I said, your object is to develop deep expertise. And at some point you are going to perhaps be asked to be an advocate for something that you actually don't think makes any sense. And that is really a crossroads point for a lot of people. I know a lot of people who have maintained their integrity. I feel I have throughout my career. And I know plenty of people who have, and they've gone on to do absolutely great things. I actually also know people who have not, and who actually have advanced because of that within their companies, but they're viewed with a certain amount of contempt by their peers, and that is not where you want to be. But it leads to a piece of advice that I actually give everybody, which is never take a job that you're not willing to walk away from. You never want to be in a position where you're forced to choose between your job and your personal integrity. And again, it doesn't happen all that much, but I've seen it happen. I've seen it happen often enough to make a point of it. Let me just give you an example. I was one of the things I got heavily involved with was high energy lasers, which I would say, has sort of been a never land for military applications for a long time. Since the early days of lasers, people have talked about everybody has this idea of a ray gun. And so there's always been these programs, trying to make that work. We have never really deployed an operational high energy laser system over the last 50, 60 years since the laser was invented. But I will say, so I got involved in particular with a program called Airborne Laser, and it was an Air Force program, and the physics problems involved were really interesting. It was a oxygen iodine chemical laser. I think that operated around 1.3 microns. Don't hold me to that, but something around there. There were issues associated with atmospheric turbulence, the phenomenology of it, optics, real-time atmospheric correction, wavefront correction. But at the end of the day, the program didn't make a lick of sense. And in fact, eventually got canceled after about $10 billion was spent on it. And, I have to say, I didn't feel sorry for the advocates for the program. But I did feel sorry for the engineers and physicists who would work so hard on it. They actually were solving some really interesting technical problems. But in that particular case, for something that really had no business flying or operating. I mean, the fundamental problem with that program was, the idea was to shoot down ballistic missiles. It actually did not have, it flew on a 747F, which was the biggest cargo aircraft available. And so the biggest laser they could put on that could not it couldn't shoot farther than a ballistic missile could fly. So the ballistic missiles could always be out of range when they boosted. And in order to be effective in Iran, I still remember showing these charts to government officials. For it to be effective in an Iranian scenario, it would have had to have been flying lazy circles over Tehran during the war. And it just made absolutely no sense. One of the options available to you is to work for a government, is to work for the government. And I'm not now talking about the national laboratories. That's a different animal. That's sort of I've already kind of talked a little bit about. But there are government labs. There's a Air Force Research Lab. There's the Naval Research Laboratory. It's really, it's important work, and it can be very interesting. I know a lot of people who do that, who are there basically to help the military services be smart buyers. But it's rarely revolutionary work. They're generally focused on specific short-term projects. And rarely get involved in anything that's more than a few years away. So, frankly, I think working at an FFRDC is far more interesting. And by the way, the pay's a lot better. You're not a civil servant. But the nice thing about working at a government lab is that you actually get to direct funding. If you're working at a national laboratory or a place like Lincoln Laboratories, you actually, at the end of the day, all you can really do is give advice, and the government can choose to take it or leave it. You can only recommend. But if you have advanced in your career, and either in the government or in FFRDC, and have developed a reputation, there's a few places where you can make a big difference. And one thing that you don't often think about, but I would like you to think about, is if you are a physicist and you got a pretty strong reputation, you can actually make a pretty big difference in policy. And the APS, for example, does policy advocacy, the American Physical Society. And frankly, if you're interested, you should probably get involved. They have a special group for that. By the way, I personally am not. But if you are, and if you're early in your career, you're not going to really have much impact, and frankly, no one's going to care too much about what you have to say. But once you get some expertise and a reputation, you can really make a big difference. And one particular thing, again, you should think about later in your career if you're interested, is the AAAS runs a congressional fellows program, and there's also a White House fellows program that exists. And you can actually have a really big impact in those jobs. I actually had the opportunity to work at the White House, and right after 9/11, and I was actually the point guy in the White House for pretty much all the research and development, along with pretty much anything having to do with weapons of mass destruction, like bioterrorism or nuclear weapons, et cetera. And then I was actually one of the 5 people who was tapped to help set up the new Department of Homeland Security, and then went over to the Department of Homeland Security. And I have to say that was probably the most intense, but also the most rewarding, one of the most rewarding parts of my career was getting that kind of opportunity. It was super fun. Although I would generally leave the house at 6 a.m. and not get home till 10 p.m. at night. It was pretty hard work. One quick anecdote about that work. I think it was like the first week I was on the job, I got invited to a meeting. What had happened was TSA, the guys who check baggage at the airports, they had just started deploying, had been piloting what's called check baggage screeners. These are screeners that when you go to an airport and you check a bag, so this is not the same thing as when you go through the passenger checkpoint. This is when you check a bag, the ticket agent takes it and it kind of goes onto a conveyor belt, and that conveyor belt then goes generally underneath the airport and goes through a long process that eventually is supposed to get it onto your airplane, supposedly. And they were doing check baggage screening, so they were putting up basically X-ray machines along that conveyor belt to look for potential explosives, and they had tested this at a facility the TSA operates up in Atlantic City that has a whole warehouse full of abandoned luggage that they use for the purposes of testing these kinds of devices. So they had deployed these things to Miami and to San Francisco in a pilot program, and they were finding that they had something like 30% false positives. And that's a big deal, because that meant that for every time they had a false positive, that meant that somebody from TSA had to take that bag off the line, had to open it and hand inspect it. So you can imagine what the workload was for a third of the luggage going through Miami, having to do that. So anyway, let me just tell you what's funny about the story. It turns out that Atlantic City has a rat problem. And so what that meant was that when people when they had abandoned luggage that they tested on these machines that showed actually very low false positive rates, they took all the food out of them. So people who had maybe packed cheese or sausages or things like that had taken all the food they took all that food out because they didn't want the rats in the warehouse to be attracted to the luggage. And so they tested the luggage without any food in them. Well, okay, so fast forward to the deployment in Miami. In Miami, if you've ever been there, it is a gateway to South America. There's actually people who come to Miami to do their grocery shopping. And so what was happening was that it turns out that cheese and sausage, many sausages have roughly the same density and there's roughly the same chemical composition as a lot of explosives. So that's what was happening, right? Was that I was the only technical guy in the room, and the only guy who realized what had happened, and I made some recommendations for how to fix it, which they didn't take, but nevertheless, it was kind of an interesting opportunity. You're sitting in there, you walk into a meeting absolutely cold. You hear a problem, you figure out pretty quickly, again, you form a mental model for what's actually going on. You figure out pretty quickly how this came about. And again, that kind of analytic background that comes with having a physics education is actually priceless in an environment like that. So anyway, that was a fun thing. The other thing that happens generally once you've gotten to be more senior is you actually come to a crossroads. And this is kind of unique to non-academic careers, I think, because what you realize is that in order to be effective, you need to get your work done through other people. That means you have to, you're not going to be so much hands-on yourself. You have to learn how to give credit. to your subordinates, and you really have to learn people skills. This is something that is very hard sometimes for physicists to do. You know, I often talk about when people ask me about HRL laboratories and my staff. By the way, this was true at Livermore also. I often tell them that although it was a bit of a caricature, my staff is kind of like the cast characters on Big Bang Theory, right? With all the social skills that those guys had. And so having them learn how to actually handle people and mentor them and do all the things you have to do to make them successful, and be willing to bask in the glory of other people's work is an important skill. That doesn't mean though that you stop applying your analytic skills or you stop learning. And assuming you've kept your reputation intact, you actually become a graybeard. If you pardon the language here, we had a phrase for that in the old days. You became what was called an old fart. And I still treasure the day that I was presented with my old fart coffee cup because I had officially become a graybeard. But basically at that point, you're being sought for advice. You're not actually getting on the whiteboard and doing the intervals yourself. In my case, I've actually had the opportunity to lead some very world-class organizations. Lawrence Livermore has about 8,000 people. HRL has about 500 people. And in both those places, the breadth of the science that's being done is vast. And you cannot expect to be an expert at even a fraction of what is being done in those places. But again, those analytical skills that you learn as a physicist can go a very, very long way. You form these mental models very quickly about what's going on, and at least it positions you to ask some pointed questions that can usefully drive the discussion. So that's worthwhile. So let me just sort of close a little bit by saying that there are sort of three career choices that a physicist can take. The first, of course, is the academic path. When I was a graduate student, that was actually kind of considered what you were supposed to do. And if you actually said that you weren't interested in doing that, then I can tell you a lot of the faculty members were not happy with that. And it's a great and noble calling. It's you're basically training the next generation. You're conducting research that is fundamental research, which is absolutely the base for which almost everything builds, on which everything is built. And there's some nice benefits, right? The work environment is terrific. You have a lot more freedom of choice in what you do, although not as much as you might think, but you have a lot more freedom of choice in what you do than you do in almost any other environment. And it doesn't hurt that the average age in a university is sort of 22, 23 years old. It's hard to not go onto a campus somewhere and not just feel the energy, right, of the place. It's a very, very good calling. But I will tell you though, the downsides are the pay is not all that great. And the tenure process can, as I mentioned at the outset of this, can be arduous and kind of capricious. You can also go into industry, and I'm not going to talk about startups. I don't know startups. I know they compete for talent. And if I was a brand new young scientist coming out of school today, I might actually, and had no family or anything, any real obligations, I might think about going into a startup. That could be a lot of fun. About 90% of them fail. I actually lose talent all the time to people who, instead of choosing to come to HRL or who choosing to come to Livermore, decide to go pursue a startup. It's kind of a sexy thing to do nowadays, but 90% of them fail. And as I said, and so what we tend to do is try to keep those connections open so that when they do fail, they can, decide on maybe a different career choice. But I'm not going to talk about talk about life at a startup. I do work a lot with Boeing and General Motors. These are really industrial laboratories. They have, each of them have their own research and development internal activities. They, again, the people who work there tend to be assigned to projects that may or may not be particularly associated with your personal technical interests. The pay is actually really, it's probably, if you go into an industrial lab, that's probably the best pay there is, if you're interested in that. But at the end of the day, if you're working for Boeing or General Motors or Google for that matter, it's really all about company value, adding value to the company. And that's actually, again, a noble thing to do, right? You're actually producing something that people want to buy. How can that not be a good thing? But it also comes with perhaps less job security than any other position. If you're assigned to a project, for example, at Boeing, if you're assigned to a satellite program, and if Boeing loses that program in a competition to somebody else, you will be cut loose. And now the good news is, and things like that, is usually the company that wins the program is desperate for talent, because they all of a sudden have an oh my God moment. I've got to go find talent. And so you can jump, and that happens all the time in industry. But nevertheless, as I said, the job security is probably the least in industrial labs like that. And then, of course, you can do what I did, which is go into either a national laboratory or one of the other FFRDCs. In those places, you have near academic job security. You really got to mess up to be asked to leave. You can either spend a career in most of these places either being very narrowly focused, or you can be like me and just kind of always enjoy, if you enjoy being on the steep end of the learning curve, you can spread your wings, and in that latter case, you'll get a lot more exposure, and it can be very, very rewarding. The downside to these jobs is that at the end of the day, you're only giving advice. Even at Livermore, when I was there, you were only at the end of the day giving advice to the Department of Energy and to Congress. And they can either choose to take it or choose not to take it. And, I'd say it was probably about 50-50. But look, if you learn a broad swath of physics and you're good at problem solving and have good analytic skills, and this is whether you're a theorist like myself, or an experimentalist, or a computational physicist, a non-academic career can be just deeply rewarding, and it certainly has been for me. So what I thought I would do is stop at that point and open it up to questions. If that works for you guys.
Yes, that's a good idea. We have about 22 people online, and some of them are undergraduates and some are graduate students, and we have some of our faculty in physics here. Well, I mean, maybe I could ask a question first, and then some other people could be less bashful and follow on questions. But you had told me that when you were young, one of the inspirations for you to get into physics was your grandfather. Mm-hmm. And well, we all have children, or at least some of their faculty do. Well, what is the best discussion line for young children in high school, middle school, to get them interested in the world of science?
Oh boy, that's a hard one. In my family, it skipped a generation, right? My grandfather was a physicist. My dad was a lawyer. And although my two uncles ended up, one of my uncles ended up as an industrial physicist working at Continental Oil. And my other uncle was a professor at Texas Christian, right? Uncle John. And none of my children pursued a scientific career. I just had my first grandchild a few months ago. I have great hopes for her, but you know, I'm not going to try to force anybody. Look, this is a big problem. Actually, it's not just about your own children. Encouraging people to get into science and technology, you know, the STEM disciplines is actually a really big issue today. Yeah, you know, part of it is role models, providing role models. So in my case, I had my grandfather, right? Now he was an academic, and he was an experimentalist. I mean, I did neither of those things, right? But there was a certain quality, as I said, to when you talk to him about how he thought about problems. And again, it's that sort of analytical way of thinking that I thought was very, very appealing to me. By the way, my dad thought it would also have been great if I had pursued a law degree, because there's some similarities, but I just couldn't imagine anything more boring than memorizing case studies at a law school. So you know, one of the things that we try to do, we did at Livermore a lot of this, and we also do at HRL, is work with the local schools. There are programs out there, for example, for junior high girls, right, to get them engaged in science. And we try to send our female staff members in there, and they show them how to build robots and do all kinds of things. You know, it may be, you know what, I'm thinking out loud here, it may be easier today than it was maybe a generation back. You know, scientists were kind of seen as nerdy and not particularly interesting and sociable.
They still do that on Big Bang Theory.
No, I know. I said, but on the other hand, Big Bang Theory did kind of make science kind of cool, right? And I also think a lot of what you're seeing now in the press, the pandemic's a good example, but other things associated with going to Mars, you know, the NASA program seems to be a bit reinvigorated. A lot of the climate change things that are going on, it's probably a little bit less nerdy, you know, and the other thing that people see is they see people like Bill Gates and Elon Musk, and who go out and make a ton of money and seem to be doing very, very worthwhile things. And so I think there are role models out there that maybe were less around a generation back. But what I would encourage, if I was trying to encourage a community to do better with with inspiring people to pursue STEM careers, the first thing is get them early, right? Junior high is a good time. You know, the other piece of advice I always give kids, and we do school tours and I talk to them, take all the math course. Actually, that was one piece of advice that I remember still from my grandfather. He said, take every math course you can take, right? And I did. I took pretty much every math course I could take. In fact, when my undergraduate degree, I actually double majored in physics and applied math. And that turned out to be a very, very good piece of advice. You know, I do think though, I mean, now I think science is not taught particularly well in schools, right? I think that's a real problem. The teachers in many cases, in many school districts, are not particularly qualified. That's a problem. You know, one thing that a university can do, or a place like HRL can do, or Livermore can do, is offer up, you know, to be a guest speaker at some of these places, to try to help with that. I actually went and saw, years ago, I went and talked to Norm Augustine, who's a very famous, you probably never heard of him, but Norm is he actually was the guy he was the first chairman of Lockheed Martin when they merged, and pretty famous policy. He was undersecretary of the Army and things like that at one point. And I suggested to him, he was on some National Science Foundation panel. I said, you know, we're teaching science is backward. we tend to start with biology, and then we go to chemistry, and we go to physics. And I said, what you really want to do is start with physics and go to chemistry and then go to biology, right? But, and at some point in time, if you ever really want me to elaborate on that, I'll be happy to do so. I think the biggest thing you can do is provide role models, right? And that means getting out, in your case, getting out into the community, right? And having science fairs and doing school tours and letting the local schools come in and maybe do a robotics competition or something like that, right? So there you go.
All right. Thank you for trying to address that question. Let's have other people ask and get input here from Parney. See what he could offer in the way of advice for your career, or what he could offer in the way of your studies.
I have this. This is an issue every time. I even at HRL and at Livermore, it was the same thing. At Livermore, I would do an all hands meeting, and I'd be in the auditorium, and it would be being broadcast across the laboratory. And I would stand there and I would finish my talk, whatever I was going to be talking about, and then I would say, "Okay, any questions?" And everybody would just kind of stare at me. And and I would tell them, I'd say, look, you don't get too many shots at me. This is your chance, right? And so, and usually there was usually one brave soul who would pipe up and say something.
Well, Terrence, I think, has a question.
Yeah, I have just a quick question. So, your talk made me think about other departments in LAS that have things going on. We have I think there's a Homeland Security degree. What are your thoughts about, putting physics, a physics major with a Homeland Security degree as a dual degree option?
Oh, that's an interesting thought. So, I mean, there's some really hard analytical problems in Homeland, right? It spans a very broad space. That's actually an interesting idea, and I think it would be unique, right, if you did that. I don't know of anybody who does that. And again, the Homeland issues tend to revolve around law enforcement, right? Primarily, but there's also a whole bunch of stuff that actually kind of gets ignored on weapons of mass destruction, nuclear, threats, bio threats. It's actually kind of funny. When the Department of Homeland Security was first started up, and I was part of that, that was actually at the forefront of their thinking, right? There were three things they cared about at the time. One was unifying the border agencies. In the old days, prior to DHS, Customs and Border Patrol and Immigration were in three different agencies. Actually, they were in three different departments. And so, it was kind of a joke, right? If you were trying to smuggle, drugs across the border, you would look for the guy in the black uniform because he was an immigration officer at the checkpoint, and you would go through there. And if you were trying to smuggle illegal immigrants across the checkpoint, you would go to the guy in the brown uniform because he was a customs agent. He didn't care about that. And so, one of the priorities for DHS at the outset was this idea of unifying the borders. But another big priority was the whole weapons of mass destruction thing. People forget right after 9/11, there was the anthrax letters that hit the Senate office buildings, and actually several people died from that. And that really focused the attention of the most senior people in our government, actually every bit as much as 9/11, the actual events of the World Trade Center did. And actually what's not widely known is that right after that happened, there was actually a nuclear hit at one of our borders, right? We had a neutron detector set up, and somebody had gone through, and whoever had set it up was just incompetent, and they could not. There was no TV cameras. They couldn't figure out what lane the hit had come from, and actually they just it never got resolved, right? It just sort of went away. People stopped worrying about it because nothing happened. But the point is that there's a lot, at the time of DHS's founding, there was a big role for science and technology. And physics in particular played a big role, certainly played a big role. I mean, I certainly felt I played a big role. And that would be, I mean, TSA has profound problems in this area. And then, of course, you know, people who do a lot of data analysis, right? There's a lot of data analysis that happens that actually, again, someone with a physics background could really contribute to. I think it's a great idea.
Yeah, about your Homeland Security. I was traveling once when I was a postdoc with an older University of Chicago professor who happened to be undergoing medical treatment at the time. And he set off all the radiation alarms at the center because he was undergoing radiation treatment for some medical reasons.
Yeah, so that, I mean, so to give you an example of an interesting physics problem is how do you deal with that, right? What you really want to do is have something with spectral discrimination available to you rather than just a simple gamma detector, right? Which is probably, he probably hit, yeah, I mean, that was a real problem. You know, everybody wanted to, I remember I was actually in the White House Situation Room in a meeting where they were proposing, the Republican National Convention and Democratic National Conventions were about to kick off, and they were going to give all the New York and Boston police these pocket pagers, which were basically just vanilla radiation detectors, right? And I was the guy in the room explaining to them that those things were just going to be going off all the time, right? Because anybody who's had radiation treatment, or frankly, if you go past a building with a lot of granite in it, or I mean, there's a lot of different things of naturally occurring radiation. Yeah, you know, truckloads of bananas, for example, would routinely set off radiation detectors at the border because they have all so much potassium-40 in them. And so yeah, so people talk about putting sodium iodide detectors into these things, and actually I think that did happen, but it's a really hard problem.
So sometimes it's a problem where we need to develop technology that doesn't exist, but we do know how to measure spectra. It's really just a matter of cost, isn't it? So how often do you run into, in giving advice, how often do you more need to make the case for an expenditure rather than, you know, advice on actual technical details?
In my case, frequently. I am frequently called in to give advice on whether a program that's been proposed should have any more money spent on it, or two, here's a problem we're trying to solve. What are the kinds of things we should be investing in, right? That happens to me all the time. And you're right. Now, one of the things I didn't touch on because of time mainly was I actually spent quite a bit of time. I spent 2 years at DARPA, Defense Advanced Research Projects Agency. And that's all about trying to create disruptive technologies to address problems that that are right now not well addressed. And I actually had quite a few programs that I started up in that arena. So it happens, right? And that again, you know, one of the things that happens, particularly when you become into that kind of position, when you get a little bit more senior, you get a bit of a reputation, is I mentioned earlier that you have to translate science into a language policymakers can understand, because they don't understand it. And actually, in some cases, they even resent the fact that they don't understand it, right? In other words, they don't like the fact that you're smarter about something than they are. Trust me, that's a problem. And so you have to be aware of that. But the other thing that can happen is you have to be able to understand what the state of the art is in some area and what the art of the possible is in some area, and then connect that to real world problems. And actually, that's a good point. It's something I should have maybe said during my talk, is that's a big part of what non-academic physicist does, a big part of it, is understanding, being abreast of the technical issues, knowing what's going on in either the academic community or the national laboratories, places like that, and understanding how that can connect to a real world problem like radiation detection or bioterrorism or whatever. It's a good point.
And a lot of physicists who actually leave the academic world go into a lot of things like in big data. It reminds me of one story that I know of a person. She was at the McGill University in Canada doing string theory, and it turns out that after her assistant professorship there ended, and you said there's a tenure problem, she went off to Ecobee, which is a thermometer company, and she's in charge of the entire database of all of that they collect from around the world from all those Ecobee thermometers. In case you don't know, Ecobee is a big competitor to Nest in thermometers. I don't know which one you have, but there's an example of big data and just using string. She was a theorist in string theory, but she happened to know how to manipulate big data and work with the engineers and the team.
Yeah, there's actually a lot of that goes on, right? If you are a experimentalist in particular, right? Nowadays, when you collect experimental data at an accelerator or I mean, you were generating terabytes of data, and you're generally looking for pretty small effects, right? And so, knowing how to do that is a skill, right? It's a skill that not a lot of people have. I will tell you though that there are limitations, there are limits to how well you can do with that, right? And I will tell you that right after 9/11, I can't tell you how many people were coming to see me at the White House pitching exactly this, about how they could have detected, how they would have picked up on the terrorists before the 9/11 event if they had all this access to all this data, right? And the reality is that, first of all, it's always easy post hoc to say that, right? Yeah, right. It's easy to know. Once you know their names, it's not hard to figure out how to go find them. And then the other problem, of course, is having actual access to data. One of the big problems with artificial intelligence and machine learning in particular nowadays is actually having access to data, right? I actually have a good friend of mine who had a chart, a view graph that I wish I keep asking her to send me a copy of it, that shows a table of when a particular machine learning algorithm was developed and when it was implemented. And it typically is years. And the reason for that is because there was no data, right, available to actually deal with that. And your Ecobee thing is a pretty good example of that. Ecobee has that data, but it's a proprietary data set, right? They're not going to give that. They're not. If that might be useful for some other purpose, right? But they're not going to give that away to anybody, right? And you can just look at what's going on with IBM Watson, right? They tried to get into the public health sphere, and they can't get access to the data. It's part of their problem. They had a lot of other issues, but that's part of it. So there are limitations. But you're right. Physicists, again, what I said at the outset, I think is very true. Physicists are really good at solving word problems, right? And they have a certain problem-solving paradigm of simplification and parsing of the problem that I don't know of any other discipline that does that, right? And it's really unique, and it's why physicists are so much in demand. Someone just sent a question about recruiters.
Yeah, I see that. Go ahead, try to answer.
Yeah, so I can answer that. I know that HRL runs recruitment fairs. I don't think we've done it at Wichita. I'm pretty sure we haven't done it at Wichita State. But we do have them, and in the short term, by the way, if anybody wants to come work at HRL, we are looking, right? We actually grew by 20% in the middle of the COVID crisis. So yeah, did well. And we're still growing. And so you can get on our right and look for jobs. But I don't know. I think if I had to guess, I would say that Wichita State is how many undergrads and graduate students do you have?
Well, there's 16,000 students.
Oh, okay. But I'm for people who are looking for physicists. Are you?
Physicists is about 60 physics majors and about 17 graduate students.
Oh, okay. So it's not that small.
It's not big though.
Yeah, I mean, look, where we tend to, first of all, at HRL, we tend to heavily recruit from the University of California schools, yep. Right? Of course. And, but we also do MIT, University of Illinois at Urbana, Wisconsin. I'll tell you what, though, I will tell my people to go look at Wichita State. And guess what? I'm actually in a position to make something happen. So
yesterday, Professor Meyer and I were in a meeting with NASA because NASA just assigned us a team of 8 engineers to do a scoping out of a new mission that I proposed. And this is a phase 2 study. And we sat down with this group of people, and one of the first things we found out is that one of these people that's on the NASA team says, "Oh, I know Wichita State. I was one of your graduates. And by the way, I know all you professors."
Oh, that's great. Yeah.
That was nice, wasn't it, Holger?
Well, I've got to believe you have a pretty good connection with Boeing, right?
Yeah, we have a connection.
Yeah.
We have a better connection with Airbus right now.
Oh, well, that's
they have good. A big, huge building on our campus.
Oh, okay. Well, boy, that's like
you see, Boeing moved out of town a little while ago.
Oh, I thought they still had a activity in Wichita.
No, they moved out of town.
Okay.
We used to get 4 funded physics majors from them, and then when they moved out of town, they canceled that also. So, yeah. But we have a better relationship with Airbus because Airbus has and Spirit Air Systems because they both have big buildings on our campus.
Yeah. So one of the questions I got that's on the chat is advice for faculty to help prepare and decide on the various career paths, especially with a focus on assuring access to students with diverse gender, racial, and other backgrounds. I think so. I think both in the national lab system, and I can tell you for sure at HRL, diversity is a big deal for us, right? And actually, for a very practical reason, I bring this up all the time when I talk to my senior staff, and I also talk to the general population. That I think there's a lot to be said about. There's sort of this ineffable creativity that you get when you bring in people from different backgrounds with different approaches to solving problems, right? That you don't get if you just bring a whole bunch. I mean, there's a lot to be said. For example, if I got a solid state physics problem with not just having solid state physicists looking at it, you know what I'm saying? And there was actually a study that was done years ago that I wish I could find it. That it was at a hospital, and they had a control group of I think oncologists, and then they had another group that was comprised of people outside those specialties, right? And the group that was outside those specialties routinely and with high levels of significance outperformed the group of experts. And it was mainly because they all approached the problem from different ways, right? And so I think that it also translates into people's backgrounds. It's not just your technical disciplines. It's also how you grew up and cultural backgrounds. I think those all things help to, and at HRL, it's certainly a big part of it. One of the problems you have with diversity in the STEM areas is the size of the pool, right? So for example, in chemistry, I believe there are more chemistry undergraduates nationally than there are female chemistry undergraduates and graduates than there are male chemistry graduates and undergraduates. But that's not true for chemical engineering. and the pool of Black students in physics is really small, right? It's way under the what you would expect from the national averages, right? And so we've tried to work with HBCUs a bit to try to offer internships and that sort of thing. But anyway, in terms of career choice paths, the first thing if you're in physics is, are you going to be an experimentalist or are you going to be a theorist? For me, it was easy. I mean, I'll walk into laboratories and equipment just stops working. So it was, it was really easy for me. And plus, I really like the math, and so I enjoyed the theoretical side of physics a lot. And of course, when I was young, the area of computational physics was just getting some legs, which is sort of a third branch, I think, right? And then, here's the thing: if you want to be an academic, if you want to pursue an academic career, you should try to pursue an academic career. I will just say that it's an arduous path to get there, right? And so you got to be willing to, spend long hours teaching and then at night doing your research and getting your grants and all the things you got to do to get tenure. And I'm not so sure. In my case, that really wasn't something I wanted to do. And then you also have to choose between like national labs, FFRDCs, and then just sort of the industrial base, going to Google or going to General Motors or Ford or someplace like that. They're all going to hire physicists. And the work, I don't find it personally particularly interesting, but I'm sure it can be. It tends to be pretty evolutionary and routine, I think. But there are always interesting problems that people have to solve. So.
All right. Well, Barney, we lost about half our audience, probably because a lot of people had to go off to other classes.
Yeah, and I actually have I have to go do some things too. So. And
we will let you go. And thank you now for contacting us. It was great to have met you again. I met you once before when Ed Hartooni, who was a Lawrence Livermore National Lab person, who was a co-spokesman with me on an experiment in Fermilab. And I met you once then. That's how I recognized your grandfather's.
Oh, okay.
Like, I know that guy. But then it turned out to be your grandfather. You have a similarity. And and so it was great to make contact with you. And we're here at Wichita State. We're excited to have had your talk. We really appreciate your time and effort to give this talk. And it makes a connection with our past because your grandfather, who was inspirational to you, was one of our former chairmen. And I found that box of photos of other things of his in my labs. So
I would offer up
a connection.
Well, it was my pleasure entirely. And I would offer up that if anybody wants to contact me or, and ask me something, you have my connection information, and they should all feel free to do so.
Okay, I'll be happy to give it out to anybody if you ask. So okay. Thank you. And well, thanks again. Bye, everyone.
Thank you. Bye-bye.
Bye.